So here we will talk about the Faraday's law again. Okay, so yeah, so the title here is induced electric field. Induced electric field. So before, when we talk about the Faraday's law on the left side, it is nothing but an E. So we call it induced EMF, induced electromotive force. Okay, so here on the left side, it becomes a line integral. So here is a line integral of E dot ds. Okay, equal this thing. Okay, so here you can see the E field here. So we call it induced E field. And yeah, so here is the highlight a changing magnetic field, which means this part, because the magnetic flux is changing, which means the magnetic field is also changing, produce an electric field. Okay, so a changing magnetic field produces an electric field. Okay, so here we have to be careful. On the left side, it is this line integral, but in chapter 24, when we talk about the electrostatics, 静电学, so at that time, when we have integration of E dot ds for a closed path, it must be zero. It must be zero at that time. So at that time, we don't consider any B field or any changing B field. So at that time, all the E field are generated by static charges for this part. Okay, it is referring to chapter 24. Okay, all the E field are generated by static charges. So in that case, when you integrating E for a closed path, it must be a zero. But here, as much as we have a changing B field, so this term is zero anymore. It's not zero anymore. So we have on the left side, this line integral equals to negative d phi b dt. So if the B field doesn't change at all, then this term will still be zero. Okay, but by changing magnetic flux, okay, so therefore, electric potential has meaning only. So at that time, we call this thing. At that time, we call V equals negative integration of E dot ds. So we call this thing electric potential. So electric potential is this thing. Okay, has meaning only for electric field that are produced by static charges. It has no meaning for electric field that are produced by induction. So yeah. So when here we will not use V for this case. We will not say, oh, this is negative V, okay, because it will make us confused. So we will make it like integration of E dot ds. Especially this is a closed integral. If we use V, so you consider going for a whole loop, it must be zero, but that's not the case. Here we have a changing B field or changing magnetic flux. Okay, so we have induced EMF, or we have an induced current, induced E field. Okay, this is the induced E field. Okay, so here we can see on the right side we have four small figure. So yeah, so here it says this orange circle means within this region we have an uniform B field pointing into the page. So we have all of these are the B field pointing into the page. And then here this red ring means this is a copper ring. This is the copper ring. And then here we assume that this B is changing or increasing. It is increasing, which means that for this cross section, okay, for this loop, for this region, so we have as much as B is uniform, so phi B will be B times A. B times A. A is the area of this circle. Okay, B times A. So if B is changing, then phi B is changing. Okay, and then it should be if B is increasing, then yeah, d phi b dt should be a positive value. Okay, so we have a negative sign. Okay, so which means that d phi b dt is a positive value, and therefore E is smaller than 0, or integration of E dot ds is smaller than 0, like this. Okay, so in this case, so here we can determine the direction of the current still by the Lenz's law. So as much as B field is pointing into the page and it is increasing, which means that or maybe using the Lenz's law, as much as the B field is increasing pointing into the page, so the loop here should generate B induced pointing out of the page. B induced should be pointing out of the page to cancel this change. So according to the Lenz's law. So using the right hand rule, your use of thumb pointing out of the page, and then your thumb will be counterclockwise, which is the direction of the current. Okay. And it also means that the E field are somehow like counterclockwise. So along this circle, okay, this E field on the left side is pointing downward. This E field at the bottom is pointing to the right side, so on and so forth. So these E field are somehow like counterclockwise. Okay, and also here shows several electric field lines. So which means that this E field is weaker close to the center, and then it becomes stronger and stronger when it's close to the boundary of the B field, and then become weaker again outside, because outside there is not any B field, and so there is not B field changing. You can you can simply imagine is that I'm not sure whether behind maybe behind we have a mathematical derivation, so we don't need to talk about it at this moment. Okay, so here we also talk about as much as we have several paths. These are 1, 2, 3, and 4. Okay, this 1, 2, 3, and 4. Okay, so we also still assuming that the B field is pointing into the page and is increasing. Okay, so for path 1 and path 2, okay, and as much as B is uniform over the whole circle region, okay, and then we assume that this path and this path is are exactly the same, with the same shape, but with different location only, and then they are also inside this yellow region. So in that case, we will consider integration of E dot ds for path 1 should be the same as integration of E dot ds for path 2, or maybe we can say this is path 1, path 2. We can use a P1, P2 to identify it. Okay, so these two should be the same. And for path 3, part of it is outside. So in that case, we will say integration of E dot ds of path 3. So this is path 3. P3. So this P3 is smaller than integration of E dot ds for path 1 or path 2. They are the same. Okay, so we'll say this one is smaller than the line integral for path 1 and path 2. And for path 4, it is all the way outside this yellow region, which means that this is also larger than integration of E dot ds for path 4. So this path 4, This is path 4, and this is actually 0 because there's no B field and no B field changing here in this region. So this one should be 0. Should be 0. Yeah, I think it should be the other way around because yeah, I think I should say this one for this one is larger. So with a negative sign, it should be the other way around. It should be the other way around. It should be like this is larger. This is larger. Okay. Because all these values are negative. All these values are negative value. Okay, so the order should be the reverse order. Okay, so here it also mentioned, okay, so for the equal EMF are induced around path 1 and path 2, which lie entirely within the region of changing magnetic field, and a smaller EMF is induced around path 3. Okay, so here, when we talk about the magnitude, so when we take absolute value, so yeah, E dot ds, so when we take the absolute value, this one, for path 1, path 2 should be larger than path 3, should be larger than path 4. But here, yeah, it should have a negative sign. It should have a negative sign. Okay, so for path 4, there's no net EMF because the path is lie entirely outside the magnetic field. Okay. Okay, so here we have a sample problem. So it says in the figure, we take R equals 8.5 centimeter, dB dt equals to 0.13 Tesla per second. So find an expression for the magnitude E of the induced E field at point within the magnetic field at a radius R from the center of the magnetic field. Evaluate the expression for R equals to 5.2. Okay, so the whole radius, capital R, is 8.5. So we would like to find the E field at R equals to 5.2. Actually, we can find the E field at any R. Okay, so we would like to use the Faraday's law. So first of all, we have an integration of E dot ds on the left side. So as similar to what we have done in chapter 29. So at that time, it is something like integration of B dot ds. So we assume many things. B is uniform, and then B and ds is parallel to each other, and then point to the same direction. So B dot ds is B times ds, and then B is uniform. We can put it outside, so it is just B times the length of the path. So here is the same case. E and ds should be pointing to the same direction, or opposite direction. So in this case, it is integration of E times ds, and then E is uniform because it is a circle. This is all the weight symmetry. So E is uniform, so it becomes something like this. And this is the circumference of a circle, so it is nothing but 2 pi r. So E times 2 pi r. So nothing but this thing. And then we would like to consider on the right side, it should be negative d phi b dt. So first of all, we would like to calculate phi b. Phi b will be b times a, because the b and a, yeah, b, phi b, the general expression should be like phi b should be integration of b dot dA, general expression. But here b and dA are parallel to each other, pointing to the same direction. So it is b times dA, and b is uniform. So it is nothing but b times a. Okay, so it is nothing but b times pi r square for a circle area. Okay, so and then we take the derivative of it. D phi b dt will be, okay, so this is constant to the time. So we have pi r squared dB dt. Okay, and actually we already know what is dB dt. Okay, so we can just plug in this one thing and two thing in the Faraday's law. So Faraday's law is integration of E dot ds equals negative d phi b dt. Okay, so on the left side it is E times 2 pi r and then equals negative pi r squared dB dt. Okay, so we can do some cancellation. Pi and pi can be cancelled. This r and one of the r can be cancelled. So it remains E equals, let me see, negative 1/2 r over 2 times dB dt. So this is the general expression when r is smaller than capital R, or smaller or equal to capital R. Yeah, because if it is outside, then d phi b, so this one should be capital R. If R is larger than, maybe in question B. So here we talk about R is smaller than capital R. So both sides are small r, then it can do the cancellation. Okay, and actually we would like to find E when R is equals to 5.2 centimeter. So we plug in E of R equals 5.2 centimeter, and then take the absolute value because we would like to find the magnitude. The magnitude. Okay, the magnitude means the absolute value. Okay, so it is nothing but 0.052 over 2 times 0.13. Okay, so this is nothing but 3.4 millivolt per meter. Originally the SI unit should be volt per meter, but it is this one is 10 to negative third power. Okay, so this is pretty easy, but actually this expression will be quite important. Okay, so here we talk about R. This R is larger than capital R. R is larger than capital R. This capital R is still 8.5 centimeter, and then we would still like to find the expression of E. Okay, so here integration of E dot ds equals negative d phi b dt. Okay, so on the left side it is still E times 2 pi r. So here this path is this one rather than the inner one. So this is the path. So this is small r rather than the inner one. Okay, and then when we talk about the phi b, it is still d times b times a, and then dt. So here when we talk about the magnetic flux, we only count this circle, this smaller circle. We only count this circle rather than the whole one, because we don't have B field here. There is no B field outside. So here it should be like d times d, and then b times pi capital R squared, okay, rather than small r squared, and then dt. Okay, so we can just put everything outside of negative pi r squared dB dt. Okay, and then still we can do the cancellation. E times 2 pi R, and then we can do cancellation of pi. Okay, and then R cannot be cancelled because one is small, one is capital. So E should be negative R squared over 2R times dB dt. So this is the expression. This is the expression when R is larger than or equal to capital R. Okay, so when R is equal to 12.5 centimeter, okay, we can just evaluate E at this point. So yeah, so negative, we don't need to care about the negative sign, we take the absolute value. So R square, R is 0.0585 square over 2 times 0.125 and then times still 0.13. Okay, so this is 3.8. Yeah, 3.8, a little bit larger, millivolt per meter. Okay, a little bit larger. Okay, so this should be easy. Okay, so next we talk about the inductor and inductance. So as I mentioned, this is the third circuit element we mentioned previously. We already talked about the capacitor and resistor. So this is the third one, the inductor. So it says an inductor is a device that can be used to produce a known magnetic field in a specific region. If a current I is established through each of the n windings, n 个圈，或者是you can consider it is nothing but turns, okay, of an inductor. A magnetic flux phi b links those windings, and in inductance L of the inductor is this. So this is like the definition of the inductor. So if you still remember, for the capacitor, C is Q over V. So this is the definition of the capacitor, and here is the definition of the inductor. So yeah, so you can consider, yeah, if we provide some charge, okay, so this is the top plate and the bottom plate. We have a plus Q, and then we have negative Q. Then there will be a potential difference across the two plates of a capacitor. And here suppose we have an inductor, or you can consider it is nothing but a solenoid. I don't know what is the difference between them. So actually it is like a solenoid or an inductor. And then if we provide some current to it, okay, of course it will just go through, and then there are totally n windings or n turns. Okay, there will be some B field generate. There will be B field, or maybe the other way around. I draw it like clockwise. So it should be the other way around. If I draw it like this, it should be the B field. So for this case, B field should be pointing downward inside the inductor. And if I draw it like this, and then yeah, this is the current direction. And then in that case, B field is pointing upward. But yeah, this is a small issue. So here in this case, it means that if we have some current going through this inductor, it will generate some B field. So across this cross section, each winding will have phi b. Phi b is like equals b times a. Okay, we assume the B field is uniform inside. So it just B times A. A is the cross-section area. So for this one is B times A, and then we have totally n windings. Okay, so for the whole inductor, it will generate n times phi b, the total flux for the inductor, and then it should be proportional to the current. It should be proportional to the current. So yeah, we just divide by I. Okay, we just divide by I. So yeah. So or here in this case, if we provide some voltage, it will have some charge. Okay, so this charge is proportional to the V. So we use Q over V as the definition of the capacitor. Here, if we provide some current, it will generate some flux, magnetic flux. So this flux is proportional to the current. So if we divide this flux by the current, it should be the definition of the inductance. And here, one important thing is that the SI unit for the inductance is called Henry. Henry, H, 1 H is like 1 Tesla meter square per ampere. Okay, so Henry is the SI unit for the inductor. Okay, so here is an interesting story. Okay, so here it says the crude, which means a 很普通的，就是很烂的，很普通的，很普通的。The crude inductor with which microfarads discovered the law of induction. In those days, amenities such as insulated wire were not commercially available. Insulated wire means suppose you have some conductor for the wire, but maybe I just use this one. Okay, so this is a wire. If we just don't just have this wire, and then we have another wire to touch it, then there will be short circuit. Or if we just use this, if we just use the wire to go like this, and then the adjacent turn will touch each other, then it will not be an inductor. So which means that we need the wire, but we actually need some insulator to wrap it. Okay, so yeah, so we need the insulated wire, so that if we make it an inductor, and so the adjacent turn won't touch each other. Okay, so it is said that Faraday insulated his wire by wrapping them with strips, strip cut from one of his wife petticoats. 就是他把他老婆的衣服就是剪成一条一条，然后去卷，就是变成这样子。OK， 所以放在这个美国这个博物馆里面。Okay, so here, so here it says, because this is actually the definition of the inductor. Okay, so you can try to explain this term. Okay, so on the top we have n times phi b. Okay, so here we can evaluate as n times phi b will be. So this is so still n is the total number of turns. Okay, so here we try to express this n by small n times the length. Okay, so n is the density of the turns, which means that the number of turns per unit length, and then times the length. Okay, so we have n times L, and then phi b is still b times a. Okay, so here we have a NLBA on the top, and then for the I, okay, and then it is actually a solenoid in chapter 29. So we have a B equals mu 0 IN. Okay, so in this case, we can just plug in B equals mu 0 In. Okay, so here, we just plug in this B to here. Okay, so here we have mu 0 In. And in that case, I and I can be cancelled. I and I can be cancelled. So here we all together have mu 0, and then we have n squared times LA. And then we just move this L to the left side. So we have, on the left side, we have L over small l equals mu 0 n squared A. Mu 0 n squared over A. So this is the inductance. Inductance per unit length divided by the length per unit length equals this thing. Okay, mu 0 is a constant, the permeability constant, 4 pi times 10 to negative 7. And then n squared is the number of turn per unit length. Okay, so this is a square, and then this is also the cross section area. Okay, cross section area, number of turn per unit length. Okay, so which means that if we would like to increase the inductance, one thing is to make it longer. But if we consider the inductance in a unit length, we still want to increase this value, we can increase the number of turn in a unit length. Okay, we try to pack more turning in unit length. Okay, and then another point is, yeah, we can also increase the cross section area, making it larger. Okay, so it really makes sense. Okay, so next we talk about one phenomenon called the self-induction. Self-induction. In Chinese, it is called 自感应. Okay, self-induction. Okay, so here it says if two coils, which we have now called inductors. Okay, so we just have 1, 2, and so here we actually have 3. So are near each other. A current in, so but actually we just mentioned these maybe 1 and 2 are near each other. Okay, so two coils are near each other. A current I in one coil produce a magnetic flux phi B through the second coil. Okay, so you can consider something like this. This is the circuit. Okay, so of course this is a battery. This is the positive side, this is the negative side. And then here we have a resistance. Okay, of course this we do not connect it directly to here. We have a pointer here, which means that this pointer can be slide to the left side or right side to make if we slide it to the right side, it make the resistance larger, and if we slide it to the left side, it make the resistance smaller, because if you still remember, R is like rho times L over A. You should still remember in chapter 26. So this is like this is called a tunable resistor. Tunable resistor. 可变电阻. Okay. Yeah. Okay. So which means that we can control this R value. Okay. So nothing special. You can just draw. Actually, if you just draw a circuit like this, it means the same thing. It means the same thing. And then we have an inductor L here. Okay, so this is actually the same thing. This thing just tell you that you can change the value of R here. Okay. So in this case, as much as we have a circuit like this, okay, this is the positive side, this is the negative side. We should have a current going like this, Okay, so here just focus on the inductor. Okay, so here let me just use red color. Okay, the current is in this direction, or actually in this direction. Okay, so according to what we have learned in chapter 29, okay, we have the Biot-Savart law or the Ampere's law. We know that this term, okay, we just consider this term only. Okay, we have a current like this. Okay, we can use the right hand rule to determine. It should generate a B field. Okay, you will use a finger for this direction, and then your thumb is pointing downward. Okay, so it means that it generates a B field pointing downward. Okay, so all this B field, yeah, we assume it is uniform, so it will go across this cross-section area, which means the second turn. So it will go through a second turn, and then at the very beginning, this current is small and then becomes larger and larger, which means that the B field is also becoming larger and larger, and so as the phi B here for the second coil is increasing for the second term. So the problem is, if the phi B is increasing, which means that d phi B dt is not zero. So according to the Faraday's law, we should have an induced EMF. So actually this B is pointing downward and increasing. So for the second turn, it should generate a B induced pointing upward to cancel this change according to the Faraday's law. So this is the idea here. Quite complicated. So we start from a current going through the first turn, and then this turn will generate B field, and then there will be a magnetic flux for the second turn or other turns. Okay, in that case, as much as this magnetic flux is changing and increasing, so it should generate B induced pointing the other way around. Okay, so this is called the B induced, and then B induced, which means that there will be a EMF will be in that direction. So, and according to the right hand rule, so the EMF is actually in this direction, which is in this direction, the other way around to this one, This is like EMF in clockwise direction. So this is also the EMF due to this one. This is a battery. You can also regard it as a EMF in this direction. But for this one, this induced EMF is in the opposite direction to it. Okay, so it's like a voltage drop across this point and this point. Usually, when we consider the circuit theory, I consider the voltage drop, but in this textbook, it's a physics textbook, it likes to call it EMF. Okay, so this is the phenomenon of the self-induction. Hope you understand. Okay, so here it also mentioned that L is like N phi B over I. So we just move the I to the right side. So we have Li equals N phi B. So it just comes from the definition L equals N phi B over I. So we have this one. And then this is the Faraday's law. Okay, on the left side, of course, this is the line integral, but here we can just simply write it as E of L, the EMF of this inductor, okay, equals negative d phi b. Okay, and actually we have n turns, so we just put this n inside. So n phi b is nothing but L times I, so it is nothing but negative d Li dt. And then L is a constant to the time, so we can just move this thing outside. So finally we have a EL equals negative L di dt. Okay, so in that case, this EL should be in this direction. This EL is in this direction. So this E is in this direction. This EL points to the opposite direction. So it's just like canceling part part of each other. And yeah, actually I'm an electrical engineer, so yeah, so I seldom use this expression. Rather than that, I always use V equals or VL equals LDI dt. So we don't have a negative sign there. So this VL means it will have a, okay, so I can just still write this is the direction of EL, and usually I will just write it as this is VL, this is the higher part, this is the lower part, and then this is the current going through the inductor. Okay, so we have VL equals LDI dt. VL equals LDI dt. Okay, this is the direction of the I, which means that if you have a you can still consider the electric potential. Okay, just now we mentioned that you need to be careful about the electric potential, but actually I mean that inside this inductor, yeah, you don't try to talk about the electric potential, but here as we talk about the lump circuit, so you can consider the electric potential at this point and the electrical potential at this point. Okay, so you try to subtract the electric potential at this point to this point, which will be the VL, and then this VL will be equal to L times di dt, L times di dt. So we don't have a negative sign here. Okay, so let me have a quick summary. Hope you still remember. For the resistor, we have R, C, L, okay, or RLC, okay. So for the R, we learned it in chapter 26. So R is the easiest one. We have the Ohm's law, which is V equals IR. So in that case, we have a resistor R, and if it is a VR, this point to this point, and then we have a current I going through, so it will satisfy VR equals I times R, or V. Okay, so this is the nothing but the Ohm's law. Ohm's law. Okay, and then next, if we have a capacitor C, we have VC plus minus, and then with a current I. Okay, so it is satisfying I equals C dVC dt. So later on you will use this one, so try to remember it. Try to remember it. Okay. And here for the inductor, we have an inductor L, and then this is a VL plus minus, and then this is I. Okay, so this is nothing but VL equals L di dt. Okay, so these are derivative. Okay, later on we'll use this to write the differential equation. Okay. And then one thing we can remember is that for the potential difference of a capacitor, VC is continuous. VC 是连续的。Maybe I can call it IC. IC is not necessarily continuous. IC 不一定连续，它可能连续，但是它不保证连续。Yeah. So as much as this thing is changing, then IC is not continuous, or this thing is jumping. Yeah. This, or maybe this thing. Yeah. This loop is changing rapidly. Then IC is not continuous. And here we can say this is IL. So here IL is continuous. But VL is not necessarily continuous。写不了。OK， 反正记住两句话。OK，VC 是一定连续，IC 不一定连续，然后 IL 一定连续，然后VL 不一定连续，就是这样。记住这个，记住这1、2、3个式子，还有这两句话。OK。Okay, so let's have a 10 minutes break.